Hi, I'm O. I will show you the application of virtual work method in determining the elastic deflection of a frame in this video. In this video, we will learn how to determine the deflection of a frame by using virtual work method. This is an example of a determinate frame. We will need to determine the horizontal deflection at C of this frame using the virtual work method. Given EI in this case is constant. The frame is having pin and roller supports at A and C respectively. This is the general analysis procedure in solving the problem. First, we need to draw real and virtual structures. Then, we can analyze and determine for internal moment equations of the primary structure, which normally represent by the abbreviation capital letter M, and virtual structure with the small letter m. Lastly, we can apply the virtual work equations as shown. The primary structure can be taken from the real structure directly, whereas the virtual structure can be drawn with several treatments. In order to draw the virtual structure of this problem, we can still draw the same geometry and support condition as of the real structure. But now, we need to remove all the external loadings. In this case, 6 kN per meter was removed. Then we need to apply 1 unit virtual load at the location and direction of the intended deflection. Since in this problem, we need to solve for horizontal deflection at C, therefore, we can put 1 kN virtual load at C horizontally. The direction of the load, either to left or right, can be assumed. In this case, we assume the deflection towards right. Positive answer for your deflection indicates the real deflection is towards right, while if negative, the vice versa. We can then proceed to analyze both structures. Here, I show you the steps to determine the support reactions for primary structure. We can solve for the horizontal and vertical dimensions of point B from point A. It can be done by using the geometry of the triangle shown. We can determine the base length of the triangle by using hypotenuse cos 45 degree and the height of triangle by using the hypotenuse sin 45 degree. Then we can apply the equilibrium equations to solve for the support reactions. It is to note that the UDL 6 kN per meter can be represented by a resultant. This resultant force can be calculated from the area of the rectangular load, which is 6 multiplied 1.8, and the distance to A is 1.8 plus 2.121 meter. This is how I determine the CY, AY, and AX by using the equilibrium equations. Similar process can be applied to determine the support reactions for virtual structure with the virtual load acting at C horizontally. Later, we can write bending equations from the cut section analysis. In this case, one bending equation can be established each for member AB and BC. In virtual work method, we need to make sure that the established bending equations apply to same range of the section for both primary and virtual structures. For example, cut section 1-1 was decided for primary structure with x1 start from A and applied for a range of 0 meter to 3 meter. For member AB, here we do the same thing to virtual structure. Besides, assume the same sign of internal moment for sections at primary and virtual structures. Let's start in writing bending equations for primary structure. For section AB, the range x1 is between 0 to 3 meter. Always consider the distance x parallel with the member. Therefore, here, only the force which act perpendicular to the section is considered. In this case, we need to resolve the AY such that it acts perpendicular to the section. The moment equation, indicated as capital letter M, is 2.48 cos 45 degree multiplied with x1. While for section CB, the x2 is measured from C, range from 0 to 1.8 meter. I do not draw the free body diagram here for this section, but consider the equilibrium of forces directly from this highlighted section. Moment equations can be written from the resultant force of UDL, which is 6x2 multiplying half of x2 acting clockwise direction, and Cy at 0.32 kN multiplying with x2 in counterclockwise direction. For virtual structure, the same section applied. Support reaction that we have obtained earlier can be put into the system for further analysis. Again, we need to resolve for the support reactions at A, and the forces that acting perpendicular to the system is of our interest. Now is your turn to solve for the moment equation indicated as small letter m for section AB for this virtual structure, and for section CB. Next, you can use the virtual work equation to solve for the horizontal deflection at C. This is how we enter the inputs into the equation. Let's start with section AB. For small m, we write the moment equations for section AB obtained from virtual structure. Then, the capital letter M is the moment equations we have obtained for section AB from the primary structure. And the range for the integration refers to the range of the section AB, which is 0 to 3 meter in this case. And do not forget to divide by parameters EI. You can also write EI in front of the integration as such. Then we can continue with section CB in the equation. Here you solve for the integration and find out that the answer is a positive value. This indicates that the deflection is toward the right, exactly like what you have assumed for your virtual load direction. Now I'm giving you a problem. What will you do if you are to solve for the rotation of C for the same frame we have analyzed earlier? What will your virtual structure look like? Well done! I hope you have understood the lesson well, and see you in my next video.